Hello, my name is Christian Hook and I'm from the ISVR at the University of Southampton in the UK. My presentation today is going to be on the control of vibration in a plate using active acoustic black holes, and I'll start with a bit of motivation behind this work and then move on to the technical aspects of the work and the results. So, to begin, for those of you who aren't familiar with acoustic black holes, they're tapered structural features that introduce a decrease in wave speed as the thickness of the material decreases. So on the left here you can see a typical acoustic black hole profile that can be used as a termination for a beam, and what happens is as the wave travels down towards this tip, the wave speed slows down, and so if you have a thin strip of damping material attached to this taper, then you get a large amount of absorption. And below that is a plot of the reflection coefficient of a taper, or in fact two tapers here, a 7 cm taper and a 9 cm taper, to demonstrate that you get these bands of low reflection which occur when the local mode of the acoustic black hole is excited. And so as frequency increases, you can see that you get more attenuation, which leaves us with a problem here at low frequencies where the acoustic black hole is not so effective at absorbing vibrations. So it's previously been shown that active control can be used to address this limitation of an acoustic black hole beam termination, and so this paper sort of follows on from that and investigates the addition of active acoustic black holes to plates to control the global vibration field. So to embed an acoustic black hole in a plate, we start with a 2D taper profile, which you can see here I've put on the diagram, and then the taper profile can then be rotated by 360 degrees to cut out a sort of dish-like structure into the plate. So in this case I've used the equation shown below the diagram to define this taper here, HR, and I've put 5 of these in a rectangular plate. So the location of these 5 acoustic black holes has been based on the layout of control actuators that can be used to successfully control low order plate modes, and the reference is shown here for that paper. I've then attached viscoelastic damping material to the curved side of the plate, and I've attached piezoelectric patches to the flat side of the plate, and because on the flat side of the plate there'll be no pre-stress on the piezoelectric patch. Both the piezoelectric patches and the viscoelastic damping material provide the damping necessary for the acoustic black holes to function well and dampen the structural response of the plate. You can see from the central diagram that the passive viscoelastic material has been applied to the full curved side of each acoustic black hole, whereas the piezoelectric patches only cover about half of the surface area of the acoustic black hole, as shown in the photo on the left. So this setup has also been implemented using a constant thickness plate, so it'll be exactly the same dimensions except there'll be no acoustic black holes embedded in the plate. However, both the damping material and the piezoelectric patches have been applied. The passive structural responses of the plates have been estimated and are presented here. So the structural responses have been estimated using an array of accelerometers as shown in the photo in the middle, so 12 of them in total, and on the left we have the structural response for the plate with acoustic black holes, and on the right we have the structural response for the constant thickness plate. So the black lines represent the plate with no treatment, so therefore no piezoelectric patches and no viscoelastic damping material, and the coloured dashed lines represent the plate with both the piezoelectric patches and the viscoelastic damping material attached. If we start by looking at the constant thickness plate structural response, we can see that the addition of viscoelastic damping material and piezoelectric patches does not change the structural response much. At some frequencies you get a bit of damping, but in general the structural response is fairly similar to the undamped plate. In contrast to this, on the left, if we look at the plate with acoustic black holes, you can see that about above 2 kHz, so roughly here, we can see that the passive performance of this plate is pretty good. You get quite a lot of structural damping from the acoustic black holes. However, below 2 kHz, you can see that the acoustic black holes aren't performing as well. And this is likely that below 2 kHz is below the cut-on frequency of the acoustic black holes. So therefore, we want to use active control to address this low frequency range. In this case, using these particular piezoelectric patches, we won't be able to dampen the first mode of the structure because it's below the cut-on frequency of the piezoelectric patches, which is 250 Hz. However, we should be able to control between 250 Hz and 2 kHz, which should get rid of these quite sharp resonances at lower frequencies. The control strategy that we're going to be implementing here is a feed-forward multi-channel control strategy, which aims to minimize the sum of the squared error signals using a filtered reference least mean squares control architecture. A diagram of the control setup is shown on the left, where the plate, which has been fixed to the box using a metal edge clamp, is driven via a stinger by this large shaker in the box. The array of accelerometers on the top, as I said before, is used to estimate the structural response, and the piezoelectric patches can be driven to minimize this structural response. So what we'll require here is we'll first require an estimate of the response between each of these piezoelectric patches and each of these accelerometers. So this is going to be our plant response, and this can be modelled using 128 FIR filter coefficients. So this will be our G hat here. And if we filter this reference signal here that we're taking from the signal that's used to drive the shaker, if we filter that signal using our matrix of plant responses, then we can obtain the filtered reference signal matrix R hat, which can be used in combination with the error signal measured from the accelerometers to update this controller W. This controller W has been set to contain 32 FR filter coefficients, and by filtering the reference signal with this controller W, we then get the control signal U, which can then be used to drive each of these piezoelectric patches to therefore minimize the error signal. To demonstrate the performance of this controller, I've implemented it by calculating the optimum set of control filter coefficients. However, in real time you'd expect to do this via an adaptive method. So here are the performance results. On the left there are two plots showing the structural response of the plates with and without damping material and piezoelectric patches attached, which I showed you earlier. And then on the right you can see two more performance plots showing the structural response when the structure is also being controlled actively to reduce the structural response between 250 Hz and 2 kHz. So if we start by looking at the response for the acoustic black hole plate, you see on the left that above 2 kHz we're getting really good performance, and below 2 kHz we're getting poor performance. When we implement control, we can now see that between 250 Hz and 2 kHz, specifically these sort of sharp resonances here and this sort of group of resonances here, they've actually been reduced significantly, and now the plate has a good broadband damping. Whereas on the constant thickness plate, which is shown below, you can see that whilst performing active control gives good reduction between 250 and 2 kHz, above this we're still lacking any sort of control of the plate, so it's not really good over a broad frequency range. And the difference between these two plates, as I've shown here in this box, is a 6 decibel reduction for the active acoustic black hole plate compared to the constant thickness plate without any treatment, and a 3 decibel reduction over the constant thickness plate with active control and treatment. So not only does the acoustic black hole plate outperform the constant thickness plate, the control effort required to implement this control is much lower for the plate with acoustic black holes. On the right you can see this diagram here, and we can see that above approximately 800 Hz, the control effort, which is essentially the energy required to drive each of these control actuators, is much lower. So the active acoustic black hole plate gives us a performance benefit in terms of the energy required to implement control and the broadband performance of the plate. So to conclude, this work has demonstrated that a hybrid control approach consisting of active control and passive damping material can be used to tackle vibration in a plate. In this case, the passive acoustic black hole effect dampens the higher frequencies, whilst active control is used to dampen the lower frequencies. This hybrid control treatment is very effective, as I showed before, requires less energy, and the performance is better than applying a similar active control treatment or damping to a constant thickness plate. The hybrid treatment is also lighter than applying a lot of conventional damping material to a constant thickness plate, and requires less energy to implement than, say, a purely active solution that would extend up to higher frequencies, which would also require a lot more sensors and a lot more actuators to identify and address the vibration problems. I hope you've enjoyed listening to my presentation. I've got my references from earlier in the presentation at the bottom, and I hope you have a great conference.